Good morning, Dr. Howard. I have a question.
Okay.
Um, do you use the same Zoom link every time? Because for some reason I didn't get the link this class. Someone had to send it to me.
It should be the same Zoom link. I just send the reminders out so people won't forget.
Yeah, I know you send those.
Kind of a little
I didn't
odd.
get it though. I don't know why. I normally get them. Okay.
Well, yeah, I mean, I don't know what to say about that, but
Okay, thank you.
you're here, so just sign in and um, we'll be good. So we'll start in a couple of minutes here. But for those of you who are here already, please come and get your exams. Geez, I've been hauling around these things for weeks now, and you need them way more than I do. I know what the questions are. You probably should get your exams so that you can review what the questions are. Okay. All right. I'm gonna share the screen in just a second, but let me ask, does anybody have another question before we get started?
Hello, Dr. Howard. I have a question.
Okay, Dwayne.
Will you be hosting office hours today? I wanted to come get my test.
I will be here all afternoon today.
Okay, got it. Thank you.
I had to delay something. I had to delay my off-campus appointment till tomorrow, actually, but I didn't find out about it until I was actually at the appointment this morning. So basically, they wasted my morning. So I'll be in all afternoon today. I'll probably be in no later than about 2 o'clock tomorrow, but I'm fairly certain that I won't be able to be here before noon tomorrow. But I'll be here in the afternoon after 2, certainly, perhaps earlier than that. And then pretty much all day Friday, except for when I'm over stuffing my face at the department picnic. Okay. So let's talk about matter in ecosystems. So as I said, there are 2 big topics, 2 big preoccupations in ecosystem ecology. And they are energy flow and matter cycling. And you'll remember that energy flows because it comes into the Earth ecosystem in the form of high energy photons, is captured by plants, and then the energy is degraded into lower energy content forms. Chemical bonds have less energy in them than the original photons, and when those bonds are broken, Generally, there's not enough energy left after some of it is used for metabolic processes to be recaptured. So it's just lost as waste heat. So energy is a one-way flow. Matter, on the other hand, is neither created nor destroyed in our Newtonian universe or Einsteinian universe. And so the very same atoms that are in your body now were in the atoms of the early Earth, and indeed were formed in the Big Bang. So they are the very same atoms. So we think about matter then in terms of cycles, and we think of them in a particular way. There's a way that has developed to conceptualize how matter moves into and out of and between different forms on Earth, and that's called the compartment model. So first we'll just talk about what a compartment model actually is. And then we'll look at the constituents of it, which are compartments, pools, and fluxes. And then we'll look at a number of the important matter cycles. And we'll use them to illustrate some of the principles of ecosystem ecology as it pertains to matter cycles. First, we'll look at the water cycle. This is an important one for several reasons, but one of the reasons is that what we call the fluxes or exchanges between compartments are balanced. So the water cycle is in balance. Then we'll look at the carbon cycle, which has unbalanced fluxes. More carbon is going from one pool to another than is coming back in the opposite direction. We'll look at three other cycles that show that illustrate matter cycles that have limited exchange between compartments, that is limited fluxes, limited pools, that means limited amounts of the element, and one in which it's pretty obvious that we don't know a lot about what's going on. And this will show you how much room there is for research in this field of ecology. We'll finish by talking about microbial mediation of these fluxes, these exchanges between compartments. These are extremely important, and we know so little about them. We exist today by virtue of our microbial friends, and only because of our microbial friends. They are responsible for making the life habitable for metazoans. And we'll look at two cycles that require microbes to convert elements from one form into another. So let's just look at what a compartment model is, and we'll pick out some of the features of it. And this will be very diagrammatic, and we won't have numbers on a lot of things, but it will illustrate what we mean by compartment models. So a compartment model then is an abstract way of thinking about elements in ecosystems. So a compartment is something that contains matter in some form. That might be living things. Living things contain phosphorus in some form. But there's also an inorganic compartment that is rocks. Rocks contain a lot of phosphorus. Water contains phosphorus, dissolved phosphorus. So there you have three different compartments that can contain elements like phosphorus, or oxygen or carbon for that matter. Now the pool refers to the amount of matter that is found in a compartment. So just because you have a compartment doesn't tell you anything about how much there is in the compartment. A pool could be relatively small. For instance, the atmospheric pool of carbon is relatively small compared to other pools. The atmosphere is, of course, a compartment. The pool that it contains is a small pool. Sedimentary rock is another compartment. And there's way more carbon in that. That's a bigger pool of carbon. Okay, and then finally, the technical term for exchange between two compartments is a flux. So that's a rate of exchange. Now, this is generally kind of generally framed in terms of rate per year, because that's something that we can actually kind of measure with reasonable accuracy. If you have very accurate instruments, you can look at the flux of carbon in leaves that are photosynthesizing, but mostly we talk about much bigger picture compartments than that, and much bigger picture fluxes. So, megatons per year, gigatons per year, teratons per year. That's how we typically talk about fluxes. So that's the rate at which an element will move from one compartment to another. And it will decrease the pool from which it is moving and increase the pool into which it's moving. So the important thing to understand is the flux between two compartments is completely unrelated to the size of the pool. You can have a lot of movement between very small pools, and you can have very limited movement between very large pools of an element. And we'll illustrate both of those things. Finally, it's very important, especially for our survival on this planet, to understand that fluxes are not always in balance. Unbalanced fluxes result in an accumulation of matter in one compartment from another compartment. So elements are removed from one compartment and accumulate in a second one. So the pool gets bigger if the flux is not balanced. And we'll illustrate that also. So, okay, we've got compartments, pools, and fluxes. How would an ecologist kind of diagram this? Okay, well, this is kind of a real schematic compartment model of the carbon cycle, which of course you can't see because this is in the way. Let me move this down. Okay, see if we can do that. Well, now you can't see the other thing, but okay, but this is compartment, pools, and fluxes in the carbon cycle. We'll look at these in more detail shortly, but just to illustrate, this is how ecologists conceive of these element cycles, these matter cycles. So here you can see that you've got biological processes kind of packaged in one area, okay? And here are the compartments. So animals could be a compartment, detritus or decaying matter could be a compartment, microbes could be a compartment, and producers could be a compartment. Now, the size of these boxes has nothing to do with the amount of carbon in them. We'll get to that later. But this just illustrates that here is how we think of these things. And you'll notice that we've got arrows indicating the fluxes from one compartment to another. So this only shows the compartments and the fluxes. It really doesn't show anything about the pools. And it doesn't tell us the degree to which these things are moving between the compartments. But you can see here that animals will eat animals. And so there's a circular thing here. Animals die and become detritus. Detritus may be consumed by animals. Plants and algae and bacteria can be consumed by animals. So these are fluxes into the animal compartment. Notice that these things can die and become detritus, and mostly detritus is decayed by microbes. So we've got an arrow going this way, a flux in this direction. Now, really, truly, microbes also die without being consumed. So there's actually going to be an arrow going back the other way. But you see how this works. We've got compartments. We haven't specified the size of them yet. And we've got these fluxes between the compartments. And we haven't specified each and every flux that is possible to have, but we have, for illustrative purposes, shown you kind of how we think about it. Now, notice that you got these biological processes and they turn over carbon quite quickly, but detritus can also be sequestered into things like fossil fuels. Okay, and once detritus is processed into fossil fuels, it tends to stay that way. So it accumulates very slowly and remains there for billions of years, unless something happens. And of course, that would be natural erosion here, or our burning of these fossil fuels. So the other thing that can happen to carbon here in these geological processes is that you can have the formation of sedimentary rocks, which contain a lot of carbon, carbonate rock, which is where most of the carbon actually is. And so it's not clear from the size of these boxes here how big the pool is. The pools are quite different in size, and we'll actually put numbers on them in a minute. But you see that carbon can be removed from sedimentary rock through erosion. It can be dissolved in water. It can be weathered into soil. Once it's in the soil or water, it can be exchanged with the atmosphere, and the atmosphere then can provide photosynthesis, raw materials for plants and algae, and the microbes, when they decay these things, can release carbon dioxide as the final product of decomposition, which can go into either soil or water. We've got a big arrow from microbes to soil, but there's also an arrow directly from microbes to atmosphere. So this is a concept. This is a conceptual framework for what we're going to see when we start putting numbers on these things. What we'll do is start specifying the compartments in more detail. We'll start putting numbers on how much is in each compartment. That'll be the size of the pool. And we'll start putting numbers on the arrows, which will show you how much is transferred from one compartment to another in the course of a single year. So, whoops, and what did we do here? We need to do this. There, okay. So this then is the water cycle. And I'm gonna move this down. So we're talking about teratons, which is 10 to the 18th grams. These are usually teratons or gigatons. Gigatons is 10 to the 15th. Okay, so this is the water cycle. And here, let me do this. So we've got these various compartments. So you have the ocean compartment, you have the freshwater compartment, you have the atmospheric compartment. There are organisms on land, although they have relatively little water. And so we don't actually have them on here specified. So what you see here is, okay, the water content of the ocean. So this is the compartment, the oceans, and here is the size of the pool. Okay, 1.4 million teratons, roughly. I'll put that back up at the top so that we can see this. Okay, and so you'll notice that evaporation from the oceans into the atmosphere accounts for 425 teratons a year. Precipitation accounts for 385. There's some transport of water vapor over land, and precipitation accounts for 111 teratons per year. Evaporation and transpiration from living organisms for 71. And then runoff and groundwater, about 40 teratons. Okay, there is some water in the sedimentary rocks. It's small relative to the amount of water in the oceans. Now let's look at the interesting features of this. First, the fluxes are in balance, but they are not directly in balance. And once again, I have to do this. In fact, more evaporation from the ocean occurs than precipitation returns. So there is an accumulation of 40 teratons of water vapor in the atmosphere from evaporation over the ocean. And that is not replaced. You don't get 40 teratons of precipitation to match what was evaporated. You get 425 evaporated and 385 precipitated back into the ocean. So there's a net loss of 40 teratons from the ocean to the atmosphere every single year. Now, the atmosphere is not accumulating water, so somehow that water's going somewhere. And here's where it goes. So that 40 teratons is right here. Oops, right. Come on, where is it? 40 teratons is right here. So this evaporation from the ocean is transported over land and falls as precipitation over the land. And notice that I think somebody needs to mute themselves there. Let's see, you have 71 teratons evaporating and being transpired by plants, plus 40 that's coming in from the oceans, and that equals this 111. So these unbalanced fluxes balance out these unbalanced fluxes. So the atmosphere gains 40 teratons a year, in addition to the 13 that it has on average, but then those 40 teratons are lost. So the net content of the atmosphere remains unchanged. You get 40 in, but then 40 falls as rain. You get 71 in, those 71 fall as rain. So notice the 40 missing teratons from the ocean are now somewhere on land. They then run off in groundwater and rivers, restoring the missing 40 teratons to the oceans. So it's indirect. This flux is not directly balanced by this flux. Instead, it is balanced by these fluxes here. Okay, so there's, it's important to understand that a flux does not have to be in balance. It can be balanced indirectly by another set of fluxes that returns elements to the original source. The other thing to understand here is this is really interesting. Notice that evaporation and transpiration over land accounts for 71 teratons out of the 111 that precipitate. So roughly 2/3 of all precipitation occurs from transpiration from plants and evaporation. And actually, we've discovered by radio labeling water in plants that water returns as precipitation within about 20 kilometers of the point at which it was evaporated into the atmosphere. So roughly 2/3 of all precipitation on land is due to the plant community that exists in the local area. That has some important consequences. If you convert one biome to another, you will alter the water cycle. If you engage in a sustained program of tree planting in a relatively arid area, and you can keep those trees alive, they will gradually transpire more and more water, and there will be more and more precipitation in that area. And the forest will become self-sustaining because it will match, the ability of the forest to grow will match the available water. Consequently, if you clear forest and plant crops, you will reduce the amount of rainfall in the immediate area. So that crop that you planted will have less water to grow on by definition, because most water is precipitated within a short distance of where it originated on land. So that's the second big message that I'd like you to learn from this. First off, we have balance in our fluxes, but they're not direct. They're indirect. The evaporation from the sea is not directly balanced. Instead, it's balanced eventually through indirect means. The second is that in the water cycle, very important, the local plant community affects the amount of local rainfall. And of course, the amount of local rainfall will then feed back and affect the plant community. So be careful what you wish for. Now, let's move on to the carbon cycle and put some numbers on the fluxes and the pools. So here is the diagrammatic carbon cycle as it was in 1981. And this is important because I'm going to show you an updated carbon cycle from not long ago. So the atmosphere contains about 640 billion metric tons. Okay, that's gigatons as opposed to teratons of water. All right, so 640 in the atmosphere, and it's fairly consistent. This is this would have to be converted from 640 gigatons into the, say, percent carbon dioxide. We're going to work on the tons of carbon here rather than other measures of atmospheric carbon. So this is kind of something to keep your eye on here. Now, notice that we have a biotic compartment, right? Here's one biotic compartment, and it happens to be the oceanic compartment. Here's a second biotic compartment. This is the terrestrial compartment. Okay, so here is where the carbon dioxide comes from. So the respiration of terrestrial organisms accounts for about 35 gigatons per year. That is matched by assimilation through photosynthesis from terrestrial plants every year. So these fluxes are in balance here. Plants comprise about 450 gigatons of biomass. Animals much, much, much less. Bacteria and fungi, we sort of don't know. And dead organic matter, we have a good idea, is about 700 million or billion metric tons. Okay, so plants, because they are the largest part of the terrestrial component, they supply most of the dead organic matter. And about 25 billion metric tons of plant material become dead organic matter every year. Well, some of that is lost to sedimentation, not a lot. Most of it is recycled into bacteria and fungi and back into animals. So this is maybe just ever so slightly less than 25. Okay, but these components are pretty much in balance. The reason we don't have numbers here on animals and bacteria is because they're really, really small compared to plants. Okay. Let's look at the aquatic compartment then. Okay, similarly, we have animals, we have plants, and we have bacteria. Notice that we don't have as much dead organic matter. In fact, that's dissolved carbon. Dead organic matter either falls out of the oceans pretty quickly and is sedimented out in the ocean floor, or it is dissolved as carbonate. So where we have dead organic matter here, we have carbonate here. So we still have 4 compartments within the big ocean compartment. We have 4 compartments in the terrestrial compartment. So here then is the exchange between dissolved CO2, about 84 goes into the atmosphere from dissolved CO2. Remember that carbonate equilibrates with carbon dioxide levels in the atmosphere. And there's a backflow of about 84. So again, the oceans and atmosphere are approximately in balance. Respiration of animals adds about 50 billion metric tons of carbon to the dissolved total. but it doesn't go directly into the atmosphere the way it does from land. It dissolves as carbonate. Okay. Notice that plants have very, very small biomass in the oceans compared to land. This is because these are algae. They do not have woody tissues, and they die very quickly. So the standing pool of carbon in aquatic plants is very, very tiny. They do a lot of photosynthesis, but they die very quickly and are turned into other tissues. So there's about 50 billion metric tons of assimilation by these guys per year. About 35 of that is transmitted to bacteria and organic forms, and the rest goes to animals as food. And so you have more or less a reasonably complete cycle here. Let's look at some of the remaining things. So here is a long-term geological compartment: coal, oil, and natural gas, or fossil fuels. Notice that less than 1 billion metric tons is added to this naturally from, from the land. And mostly in the oceans, we don't get the formation of coal, oil, and natural gas in large amounts. Instead, mostly the dissolved CO2 is laid down as carbonate rocks. Okay, so there's some deposition of carbonate rock, there's some dissolution of carbonate rock back into the ocean. These are approximately in balance. Okay, volcanoes here contribute about 2, and it's kind of iffy. These numbers were not terribly well worked out in 1981. The volcanoes were, but in fact, the absorption here of carbon into dissolved forms from the atmosphere probably balances that out. Okay, here's an addition though. Combustion. This is our activities as of 1981. Okay, so atmospheric inputs are unbalanced. There should be carbon accumulating in the atmosphere. Okay, but the ocean deposition is probably responsible for balancing the input from volcanoes. At least that was our thought in 1981. Okay, so these last 2 fluxes are really tiny. They represent the weathering of rock into soil that can be used as a source of carbon for plants. And here's the very, very small accumulation of carbon on land as carbonate rock. All right, so pay attention to these numbers here. Atmospheric carbon, notice the combustion part, notice these. So just keep this kind of in the back of your mind. This is 1981. Let's look at how things have changed since then. And of course, now I'm going to move this back. Okay, and advance this way. All right, so this is as of 2011, 30 years later. Atmospheric fluxes are unbalanced, and they're more unbalanced than they were in 1981. Okay, so let's have a look. So atmospheric is still 640. Yay. That's because the accumulation of carbon in the atmosphere is so tiny in proportion to how much is there that it doesn't register very much when we look at billions of metric tons. However, this is a very small input into the atmosphere that has very big consequences. So let's look at some of the fluxes and pools. Limestone and dolomite still 18 million. Dissolved organic matter still 1.5 million. These numbers have not changed. Algae is still 5. Assimilation is still 50. Dissolved total carbons. These have not changed. Nothing in the oceans has really changed. This is fine. Sedimentation still accounts for about less than 1 here. Limestone rock production accounts for a very small amount here, and dissolution into soil accounts for a very small amount. So this whole thing, from the exchange to assimilation to algae, sedimentation, coal, all of these boxes down here, all of these compartments and all of these fluxes are the same. Let's go to terrestrial issues here. Here's plants 450, animals and bacteria still don't have enough biomass to register. Dead organic matter still 700, yay. Animals are still respiring about 35. Photosynthesis is still accounting for about 35. Volcanoes are still putting in 2. Here's what's changed: combustion. We are burning 7 times more fossil fuels in 2011 than we were 30 years previously. Half of all carbon emissions in the history of the human species have been added to the atmosphere in the last 30 years. And their full effect will not be felt for another 50 years. So what you are feeling today with the storms and the severity and the heat waves and the droughts, that is the result of carbon that was put into the atmosphere in 1970. It takes that long for the full effect of carbon to be felt. If we went to 0 net emissions today, the weather would get worse for the next 50 years. Just think about that. It's not enough to get to net 0 carbon. We have to pull carbon from the atmosphere. We have to do it as fast as possible. That's a pretty serious thing to consider, but that's why we present the carbon cycle. It is really critical. All right, so here's a review of carbon storage in the global biomes. This has a little bit more precision to this than the diagrams that we showed when we were talking about energy. They differ a little bit because energy is bound up in lots of different compounds, and we're going to focus exclusively on carbon storage here. So here's the productivity of different biomes. Here's the biomass in those biomes per square meter. And here's the length of time that the carbon, very specifically, rather than the energy, stays bound up in these biomes. And you can see that, pretty close, the forest biomes match pretty closely the storage of energy. It was about 20, 25 years in the previous presentation slide. It's about that here. Okay, and then once again, this is because the carbon is bound in woody tissues. Again, in aquatic environments where there are no woody plants, carbon turns over almost immediately. Okay. Lakes and streams, that's algae. This is algae. Basically, in the open ocean, carbon turns over in 9 days. That's why there's so little standing biomass of algae. There's tremendous production, but the algae live for only a few days and then they die and turn their carbon back over. Okay, temperate grassland is water limited. Desert scrub doesn't store a lot of carbon and doesn't have high productivity, but because there's so little water, decomposition occurs very slowly by comparison. So basically the message is, if you want to buy time, if you want to bleed carbon out of the atmosphere, reforestation is a real help. We now have carbon capture plants, but they're only doing a small amount of work compared to what we could achieve if we had a large-scale reforestation effort. So these first 2 columns match pretty well with what we talked about last time in terms of energy. It's very close. The transit time is also kind of approximate. It's a little different because we're talking exclusively about carbon rather than total energy. And I keep having to do this. Okay. So moving on. All right. So we've got the water cycle and the carbon cycle. Let's examine the dynamics of carbon in geologic history and figure out how we got this where we are. All right. Well, okay. So let this be the current level of atmospheric carbon. 450 million years ago, there was over 20 times more carbon in the atmosphere. Ooh, where did it all go? You can see that about 450 million years ago, carbon in the atmosphere took a nosedive to very low levels that are about where we are today. And notice that we had an increase, but then a steady decline. Okay, and then what's this? This is the Eocene temperature maximum. This is 4 degrees centigrade hotter than it is currently. In the Eocene temperature maximum, there were palm trees at the North Pole. So just keep that in mind. 4 degrees centigrade, when you're thinking about global climate change and people talking about 1.5 degrees, 3 degrees, 7 degrees, 4 degrees centigrade, palm trees at the North Pole right there. And really rough conditions closer to the equator. So how did we get here? Yay. Well, as it turns out, this is due to living things. Atmospheric carbon levels are regulated by feedback with living organisms. And why at 450 million years ago did we see that nosedive? Because terrestrial forests began growing. Plants colonized the land. Here are some measures that allow us to estimate how extensive terrestrial forests were. Notice that clay in the soil goes from 0 to about 0.25%. This is all due to plant material accumulating in the soil. The rooting depth based on fossils that we can find in ancient soils, rooting depth increased to like 1 meter. That means that these are really, really large plants. These are forests. These are just like, very small things. They're not, the closest thing to what we have today would be horsetails, which are tiny, tiny plants. But these are forest trees. Here's actual fossils of stems and trunks. And here's the diameter. Look, these are huge. Remember, 2 meters across is as far as you can stretch your hands from one side to the other. That means these are very, very large trees. They are removing teratons of carbon from the atmosphere. Here's the accumulation of carbon in coal. And notice that there was very little coal before terrestrial forests, and it radically increased. And as a result, atmospheric carbon took a nosedive. It's terrestrial forests. That's what is responsible for the carbon in the atmosphere today. That's what bled all the carbon out. Now, let's turn our attention to 3 other cycles to illustrate some things. So first off, the nitrogen cycle. There is actually very little nitrogen on Earth, but the rate of exchange is very, very high. So in the oceans, you see that we have only about 6,000 gigatons, right? And in the carbon cycle, it was like 1.5 million. So much less nitrogen out there. Notice that there's about 50, there's about 50 gigatons exchanged directly to the atmosphere in the form of N2, some bearing and sediments here. And here's denitrification. This is microbial activity. So microbes put about 110 gigatons of nitrogen in the atmosphere about 30 are fixed. So there's a net accumulation of 80 here. So where's this net accumulation in the atmosphere go? Well, okay. So a little of it goes over here, and there's a lot that's fixed on land. More is fixed on land than is put into the atmosphere. Okay. Lightning, it fixes about 20. So there's about 20, there's about 30 out of the 80. There's about, that's still missing from this 30. And we don't have this completely balanced, but notice that compared to the size of the biggest pool, these fluxes are big, okay? There's a lot of human nitrogen input into the atmosphere and into land. So organisms are putting some of that nitrogen into soil. A lot of the rest is running off, and soil nitrogen is increasing in many places around the world. So we don't have a perfect balance here. That's partly because of the uncertainties around human activity. We know that most of this 110 is bled out by fixation, either on land or ocean, or fixed by lightning, or absorbed by organisms. We don't have it exactly in balance. But the key thing here is not that we don't have it in balance. The key thing here is that's the biggest pool. This is a really large flux compared to the size of that pool. So nitrogen moves around very easily. There's not much of it, but it moves continually. Okay, so if we run short of nitrogen for fertilizer, well, it's likely to be rapidly replenished by these rapid fluxes. Here, on the other hand, is the phosphorus pool. And the phosphorus pool is immense, but the fluxes are tiny. All right, look at this. 840 million gigatons are bound up in sediments. But look at the fluxes. Here, look, flux from ocean to atmosphere, and from atmosphere to ocean, tiny, really tiny. Here's deposition of phosphorus over land, and here's the organisms putting phosphorus compounds back into the atmosphere, tiny. There's about 19 million gigatons, or 19,000 gigatons in mineable rock. Freshwater has about 90. Look, for all of our fertilizer accounts for 14. There is not a lot of phosphorus out there. Phosphorus is far more potentially limiting to us than nitrogen, simply because the fluxes are so minuscule. If we use 14 gigatons a year for fertilizer, how are we going to replace that? There's only a net deposition of 1 gigaton from the atmosphere. We have to mine it, or organisms have to produce it, and they produce it in very small amounts. Phosphorus is far more limiting to human activities than nitrogen is. There's not much nitrogen, but it moves around quickly. There's tons of phosphorus, but it doesn't go anywhere. So it's highly limiting. All right, here then is the last of the three. It's the sulfur cycle, and we don't know a whole lot about the sulfur cycle. You can see that this is very incompletely filled in. We don't know how much sulfur is actually in the ocean. We do know that there's about 28 gigatons of sulfide produced by the ocean, but what the standing amount is, we have no idea. We have only partial fluxes from these things, and there's some compartments that are kind of missing altogether. We don't know anything about aquatic organisms. We don't know very much about sulfur content of rock in any form. So the fluxes are not completely known. We don't really know what's going on with sulfur very well at all. And I think it's really interesting that some of the most crucial things for the survival of humanity are these fluxes of elements. Sulfur is a critical nutrient, and we don't know how much we got, and we don't know how much we're going to get. So these are critical areas of research. Okay, I'm going to finish up in a minute or two here. And what we're going to do, oops, no, we're going to go there. All right, I said, and I alluded to in one of the cycles, that microbes are responsible for the fluxes in some of the cycles. That's particularly true in the nitrogen cycle and the sulfur cycle. So here's how nitrogen is regulated by microbes. Okay, inorganic nitrogen in the atmosphere is N2, right? Okay, well, organisms can't use N2. Organisms can use nitrogen that is made available to them through oxidation reduction reactions, which is what we're doing here. So this is the most oxidized forms of nitrogen. Here are the most reduced forms of nitrogen. If it's reduced, it has hydrogens. If it has oxygen in it, it's oxidized. Here is atmospheric nitrogen. Atmospheric nitrogen can be fixed into ammonium by a number of bacteria. They gain energy from those reactions. Okay, interestingly enough, ammonium can be nitrified by other bacteria, and they gain energy from this conversion. It can be converted from nitrite to nitrate by these bacteria, and they gain still more energy. So far, so good. These bacteria gain energy by taking atmospheric nitrogen and converting it to this. These guys gain energy by converting it further. What the real interesting thing is that you can gain energy by denitrifying it as well. You can take these oxidized forms and put them back into more reduced forms. And there are other bacteria that specialize in that. So here's a bacterial loop. And at each step, the bacteria are gaining energy, and the forms of nitrogen are just ping-ponging from oxidized to reduced, oxidized to reduced. Okay, now ammonium is one of the forms of organic nitrogen that can be absorbed by plants. Nitrate and nitrite are the other forms that can be absorbed by plants. When they're absorbed by plants, they are reduced into ammonium, and that's basically the currency that plants use to make their tissues. But this is cool because you have aerobic bacteria that gain energy from these oxidation reactions, and you have anaerobic bacteria that gain energy from reduction reactions. So the nitrogen cycle is completely regulated by bacteria. The availability of nitrogen, the high flux of nitrogen, depends on these guys. We know next to nothing about them. Here are the root nodules of some ectomycorrhizal bacteria that fix nitrogen. And here are some more free-living bacteria that fix nitrogen in the soil, but don't kid yourself, we don't know very much about this. There's one other cycle in which bacteria play a big role, and it's the sulfur cycle, and it's the same thing. There are anaerobic reduction reactions that allow these bacteria to gain energy from taking oxidized forms of sulfur and turning them into reduced forms. There are other aerobic reactions that allow these aerobic bacteria to gain energy from taking the reduced sulfur compounds, turning them back into oxidized compounds. Okay, so the forms of sulfur that are most available to plants are things like H2S and ferric sulfide. So these oxidized things are reduced when they are absorbed by bacteria and plants, and they are turned into the currency through which organisms make sulfur-containing compounds. But again, we know next to nothing about these bacteria. But aerobic oxidizing, anaerobic reducing. Remember, aerobic means that you're breathing oxygen. So you're incorporating oxygen. Anaerobic means that you are doing this in the absence of oxygen. You're incorporating hydrogen and releasing oxygen. Okay, so take-home message. This is a hugely important area of ecology for human survival. We know almost nothing about some of the most important features of these element cycles. And we are about done here. I am running over just a little bit, so I'm going to stop this share. Thank you for sticking with us. If anybody has questions, please go ahead. Otherwise, I will go grab some lunch and be back in here for you to pick up your exams. So anybody?
Dr. Howard,
Yes.
just to clarify one thing, the last two labs, they're due this Friday, correct?
They're due Friday, yes.
Awesome.
You have not turned in one of the earlier labs. Your deadline is Friday. Okay,
Oh,
so
I thought you were talking to me. I was like, did I miss a lab?
some people have not turned in their earlier labs, and the deadline for all labs to be received is Friday.
Awesome. Thank you.
Okay. All right. I will see some of you after lunch. See you soon.